Greetings everyone. Today we are going to learn about convolutional neural networks, a revolutionizing machine vision in the topic of machine learning. Convolutional neural networks, CNNs, represent a pivot class of deep neural networks specifically engineered for processing grid-like data with a primary focus on images. Their emergence marked a significant turning point in computer vision, leading to unprecedented breakthroughs since their notable success in the 2012 ImageNet competition. This innovation has toppled the image recognition market, which is now projected to reach an impressive 59 billion by 2027. The rise of CNNs beyond traditional neural networks. High dimensionality, spatial relationships, and human visual cortex. Coming to high dimensionality, traditional artificial neural networks, which are ANNs, struggle with images data high dimensionality. A modest 100 into 100 pixel image, for instance, translates to 10,000 inputs, demanding millions of parameters for ANNs. Spatial relationships. CNNs inherently exploit spatial relationships and local patterns within images, a capability largely absent in traditional ANNs. Coming to human visual cortex, CNNs cleverly mimic the hierarchical processing observed in the human visual cortex, allowing for more intuitive and efficient image understanding. The core components of ANNs, which are called the CNN architecture. They are sequential layers, fully connected layers, convolutional and pooling, and hierarchical learning. Coming to sequential layers, CNNs are built from sequential layers that progressively extract more complex features from the input data. The fully connected layers. These are followed by the fully connected layers responsible for the high-level classification based on the extracted features. Convolutional and pooling. The architecture typically includes convolutional and pooling layers for feature extraction, identifying key visual elements. Hierarchical learning. The structure enables hierarchical learning, starting from basic elements like edges and progressing to complex objects. The convolutional layer, featuring extraction powerhouse. The convolutional layer is where the magic of feature extraction begins. It applies learnable features, filters, also known as kernels, across the entire input image. Each filter is meticulously designed to detect specific features ranging from simple edges and corners to more intricate textures. A remarkable advantage of this layer is its parameter sharing mechanism, which significantly reduces the total number of network parameters. Common examples include 3 into 3 filters for detecting edges and 5 into 5 filters for recognizing textures. The pooling layer, which is the downsampling and invariance. The pooling layer serves a crucial role in reducing the spatial dimensions of the feature maps generated by convolutional layers. The most common type is max pooling. Average pooling is another variant, taking the advantage value average value instead. This downsampling process offers several key benefits. It helps the CNN achieve translational invariance, meaning the network can recognize an object even if it's slightly shifted within the image. For example, a 2 into 2 max pooling layer will effectively halve the dimensions of a feature map, reducing the amount data by 75%. The fully connected layer, classification and output. Flattening, dense layers, high-level reasoning, softmax output. Let's see into this. Flattening. The final pooled feature map is flattened into a one-dimensional vector, preparing it for high-level processing. dense layer. This vector then connects to one or more fully connected dense layers which are responsible for integrating the extracted features. High level reasoning. These layers perform the high level reasoning and classification, interpreting the patterns identified in the earlier layers. Softmax output. The output layer frequently employs a softmax activation function for multi-class classification, converting raw feature insights into probability scores for each possible class. Key advantages of CNNs: parameter sharing, translational invariance, hierarchical feature learning, superior performance. Coming to parameter sharing, CNNs drastically reduce model complexity and memory footprint by sharing weights across different locations in the input, making them highly efficient. Translational invariance, a core strength allowing the convolutional neural networks to recognize objects effectively even when they are shifted, rotated, or scaled slightly within an image, without needing to relearn the feature. Hierarchical feature learning. The layered architecture enables automatic learning of increasingly complex features, from basic edges in initial layers to sophisticated object representations in deeper layers, directly from raw pixel data. Superior performance. Their effectiveness on visual data is unparalleled. Since 2012, CNNs have consistently outperformed traditional methods, demonstrating over 10% accuracy improvement on challenging benchmarks like ImageNet. There are many more advantages of CNNs, the convolutional neural networks, which are not mentioned in this. There are many more to written down. The real world applications, which are transforming industries of the convolutional neural networks. Image recognition, powering features like Google Photos, achieving remarkable accuracy. Example, 95% in object identification. Medical imaging. Model medical imaging, revolutionizing cancer detection with convolutional neural networks matching dermatologist accuracy in skin lesion classification. The main and important one, self-driving cars, enabling real-time object detection for systems like Tesla Autopilot, boosting approximately 99% precision in identifying the road objects. Facial recognition, integral to biometric security and surveillance, exemplified by Facebook Deepface 97.35% accuracy. Natural language processing, the NLP, extending beyond vision. Convolutional neural networks are also applied in text classification for tasks like sentimental analysis, outperforming certain recurrent neural networks in specific scenarios. The challenges and limitations. Though the convolutional neural networks have many advantages and applications, they also have slight challenges and limitations to it. Data dependency. Convolutional neural networks typically demand vast amounts of high quality labeled data for effective training, which can be a significant hurdle. Computational cost. Training large scale convolutional neural networks is incredibly resource intensive, requiring substantial computational power and often leading to high costs. Interpretability. Often referred to as black boxes, convolutional neural networks can be challenging to interpret, making it difficult to understand the internal decision making processes. Adversarial attacks. The convolutional neural networks are vulnerable to subtle, intentionally crafted input perturbations that can cause them to misclassify images, posing security risks. Generalization. They frequently struggle with strong generalization to entirely novel or out of distribution context, limiting their applicability in highly unpredictable environments. Future trends and conclusion. As we look into the future, several trends are shaping the evolution of CNNs. Explainable AI, a growing focus on developing methods to unravel and interpret the complex decisions made by CNNs, fostering greater trust and transparency. And such trends are edge computing, generative adversarial networks, self supervised learning. In conclusion, convolutional neural networks remain absolutely fundamental to the capabilities of artificial intelligence, particularly in visual understanding. They continue to drive innovation and transformation applications across numerous sectors, solidifying their role as the cornerstone of modern AI.